Think about this for a moment. You walk into a room, you flip a switch, and instantly the light turns on. You do this every day, at home, at work, every day, without thinking twice. But what actually causes that lamp to turn on? We call it electricity, but electricity itself is something you can't see. You don't see electricity, you only see its effects. Light, heat, movement. A lamp glowing, a motor turning, and a device coming to life. All of this happens because of electricity. And that brings us to the big question, what is electricity really? If we can't see it, how can something invisible create all these effects? Inside a lamp, inside a motor, and inside every electrical device, something is moving. Something very small, something we can't see. So if we want to understand how electrical devices work, even at a basic level, we have to start from the beginning. That's why I'm starting this new playlist called Electric World Basics. Here we'll build a simple and clear understanding of electricity step by step. So let's start with the simplest and most familiar example of all. What is electricity? You flip a switch and the lamp turns on. Why does it light up? Because the switch closes a circuit, a complete loop. Something can start moving all around the loop, through the lamp and back again. So a loop is what makes it work. But now the next question is, what is actually moving in that loop? When the loop is closed, tiny electric charges inside the wire can move. These charges pass through the lamp and make it light up. Okay, so moving charges can turn the lamp on. But what are these charges and where do they come from? To answer that, we need to zoom in on the wire, all the way down to the atoms. Everything you see, metal, plastic, even your body is made of atoms. Atoms are extremely small, so we can't see them directly with our eyes. So to understand what's happening inside the wire, we'll use a simplified picture of the atom called the Bohr model. It shows an atom like a tiny solar system, a center and particles around it. Each atom has three main building blocks: protons, neutrons, and electrons. Protons sit in the center of the atom, in the nucleus, and they have a positive charge. Neutrons are also in the nucleus, but they have no charge, they are neutral. And electrons stay around the nucleus in energy levels called shells. Inner shells are lower energy and closer to the nucleus, while outer shells are higher energy and farther out. Electrons have a negative charge. This atomic setup leads to the most important idea about electricity. What element an atom is depends on how many protons it has in its nucleus. That's why every atom of the same element has the same number of protons, which is called the atomic number. Now protons carry a positive charge and electrons carry a negative charge. In a normal neutral atom, those charges balance out because the number of protons and electrons is the same. So the atom has no overall charge. Protons and neutrons stay locked in the nucleus, but electrons, because they are much lighter, can move from one atom to another. That movement of electrons is what forms an electric current. If an atom loses electrons, it becomes more positive. And if it gains electrons, it becomes more negative. Now, if electrons can move from one atom to another, here is the next question. Why do they move easily in some materials, but not in others? Because not all materials hold their other electrons the same way. In metals like copper, the outer electrons are held weakly because they are farther from the nucleus and don't feel its pull as strongly. The closer an electron is to the nucleus, the stronger the attraction. So in copper, some electrons are not bound to a single atom. They form a shared cloud of electrons that move through the metal. As a result, inside copper, there are lots of free electrons ready to move. But in materials like plastic and in gases like helium, the outer electrons are held very tightly to their atoms, so there are almost no free charges available to move. This is where we meet two very important words in electricity: conductors and insulators. A conductor is a material where electrons can move easily, so electricity can flow through it. That's why metals like copper and aluminum are used for wires. An insulator is a material where electrons are held tightly, so they don't move easily. Insulators strongly resist the flow of electricity. That's why plastic, rubber and glass are used as protection to keep electricity only where we want it. Now that we know what conductor and insulators do, we can explain something almost everyone has experienced. Have you ever walked on a carpet and then touched the metal door handle and you get a little shock? That's static electricity. When you walk on a carpet, friction can transfer electrons from one material to another. As a result, your body can end up with extra electrons, or fewer than usual, which means you become electrically charged. Because carpets act like insulators, that charge doesn't flow away easily, so it can stay on you for a while, so you build a charge imbalance. And nature doesn't like imbalance. It always tries to return to neutral. So the moment you touch a conductor, like a metal handle, electrons suddenly jump across the small gap of air between you and the metal to balance the charge, and you feel that shock. Static electricity is one quick, uncontrolled movement of electrons that most people have experienced. And it teaches us one key idea: charges move when there's a path. In the carpet example, the path appeared suddenly and we felt a shock. But in an electrical circuit, we do the same thing on purpose and in a controlled way. So now let's go back to the lamp circuit. We build the path with wires and we use a switch to open or close that path whenever we want. The wire is a conductor, so electrons can move through the wire, pass through the lamp and return to the source. And that controlled movement is what makes the lamp produce light. But notice, they only move when the path is complete. If the switch is open, the path is broken, no complete loop, so the electrons can't travel through the lamp. Now here's the next important question. If electricity is electrons moving, what makes them move in the first place? Who starts the movement? A battery can do it. And the grid can do it too. Let's see how. As you know, copper wire is made of copper atoms, and copper naturally has electrons that can move around inside the metal. So the wire is like a tube that is already full of electrons. A battery has two terminals, the negative side and the positive side. Think of it like this. The negative side is the push side. It wants to push electrons out. And the positive side is the pull side. It wants to pull electrons back. And here is the key point. This push and pull, what we call voltage, is already there even when nothing is turned on. When the switch is off, the path is broken. So even though the push and pull exist, nothing moves because there is no complete loop. Like a water pipe with a closed valve, pressure exists but there is no flow. Now when you flip the switch, you complete the loop, and then the electrons that are already inside the wires can move from the push side through the lamp and back to the pull side. This also explains something important, something that can be dangerous. If you connect the source directly with a wire without a lamp or tiny load, electrons rush through too easily. That's called a short circuit. And because the current becomes very high, wires can heat up fast and damage equipment. That's why we use fuses and breakers. They disconnect the circuit when the current becomes unsafe. Alright, today we answered the big question, what is electricity? It's electric charge moving through a circuit, and in metal wires, that moving charge is mainly electrons. The best part is you don't need heavy theory to understand it. Just remember, a path, a movement, and an effect. In the next video, we'll explain the next big idea of the electric world step by step. Thanks for watching, and I'll see you in the next video.